All right, so we're going to take a look first at transformations of exponentials. So we're comparing our base function is 4 to the x, and then we have y equals negative 4 to the 2x plus 1 minus 5. So first thing, how many transformations do we have in that problem? Layla, what do you think? How many transformations?
4.
Yeah, we have 4. Okay, there are 2 that are going to affect the horizontal and 2 that are going to affect the vertical. What number are we going to focus on for our first transformation? Maria.
Is it the 2?
The 2 is going to be for our second transformation. Well, the 4 is the base. The negative we are going to look at, but that's on the outside. So we're not going to get to that until we do everything on the inside first. So the negative is the third transformation. Yep.
The 1?
The plus 1, yeah. So what does a plus 1 do? Yep.
Shift it left 1.
That's going to shift it left 1. Yep. So shift left 1 unit. And now for our second transformation, we are looking at the number in front of the x. What kind of transformation does the 2 cause? Yep.
Horizontal stretch.
By what?
Factor of 1/2.
Yes. So it's a horizontal stretch by a factor of 1/2. Okay, now the 4, that's not really part of anything. That's just the base. But we have, it's like a negative 1 being multiplied in front of the 4.
No, let's know he's wrong.
What's the negative in front of the 4 going to do? Yeah.
Reflect it over the x-axis.
Yep, it's a vertical reflection, which means reflect over x-axis. And lastly, the minus 5 is going to do what? Yeah.
Shift it down 5.
Shift it down 5. Yep. Okay, so that's describing the transformations of an exponential. You could have at most 6. This one had a lot. It had 4, but it didn't have all. Yes.
So for the negative 4, the only thing we do is just reflect.
Yeah. So the 4 isn't really part of anything. That's just the base. So you could, think of it as. Think of it like that. The 4 is just the base. The negative causes the reflection. If you had another number in front with it, like negative 3, now we would have to add a transformation and say vertical stretch by a factor of 3, then reflect over the x-axis.
That's what
Yeah, so that 4 is just the base. Okay, so the second one we're going to look at is determining if an exponential function is either growth or decay. All right, so let's start with f of x. Would f of x be exponential growth or exponential decay? Yeah. Yeah, how do you know that that's growth?
Because 1.2 is greater than 1.
Yeah, the base is bigger than 1. Yep. So bigger than 1, it's exponential growth. How about g of x? 3/2 to the x. Yep.
Growth.
That's also growth. You'd have to think of it as a decimal, but it's 1.5. So that's growth. And how about h of x? That one would be, yeah.
Decay.
Yep, that's decay because the base is smaller than, it's between 0 and 1. So any questions on identifying if a function represents exponential growth or exponential decay? All right, so the next one, bless you, we're going to look at is solving a inequality, exponential inequality, graphically. So to solve that, first thing we'll do is graph it. So just so we remember which one is which, the blue one is the 2/3 to the x, and the red one is the 3/4 to the x. They're both examples of what kind of exponential function? They're both, yeah.
Decay.
Yeah, they're both decay. One of them is going to decay at a faster rate than the other because of the difference in the bases. And we are looking for where the 2/3 to the x, which is the blue graph, is greater than 3/4 to the x, which is the red graph. What do we have to figure out on the calculator to be able to answer that question? Something we have to calculate.
The intersection.
Yeah, we got to first calculate the intersection. Once you know the intersection, it's either everything above it or everything below it. Just depends on which one. Okay, so we've got the intersection point. And we want to pick all numbers that are greater than 0 or all numbers that are less than 0 for the blue graph to be above the red graph. Yeah.
Less than?
Right, we want all values less than 0. That's the area where the blue graph is above the red graph. Okay, right in there. So it's every value of x less than 0. Any question on solving something like that graphically? Because when you go greater than 0, then the red graph goes above, and that's not what we want. We want the blue graph above. All right, so next question we're going to look at is an exponential word problem. Specifically, this one is decay, and we know that because it says population is decreasing, and it's by a percentage. So they want us to do 3 things. Find a formula that represents the situation. Use the formula to predict the population after 10 years. And then how long is it going to take for the population to drop to 12,000 people? All right, so we've got an amount of people. And the amount of people will be a function of how much time has passed. When you do an exponential decay model, what's the first thing you write down after the equal sign? Yep.
The starting.
Yep. And what's your starting population here? 20,000. What goes in parentheses next to the initial amount in an exponential decay equation? It's like a formula you have to put there. Yeah.
1 minus R.
1 minus r. We just got to be careful. Remember, r has to be a decimal, not a percent. They'll give it to you as a percent, but you have to change it. So what is 3% as a decimal? Yep.
0.03.
What is it?
0.03.
Yeah, 0.03. And now we have to fill in what Layla just said there, 1 minus r. So what's 1 minus 0.03? Right, it's basically how many people you're left with each year, 97%. So 0.97, and don't forget your exponent of t. Okay, so that's the first part. Find an exponential model for the situation. Okay, next part, find the population after 10 years. Where would the 10 get plugged in? There's only 2 places, yep.
T.
T. 10 years is a time. It's not an amount of people. So we're going to plug in 10 for T. So we'll do 20,000 times 0.97 to the 10. Now that doesn't require a logarithm because we filled in for the variable. There was no variable exponent anymore. So after 10 years, we'll be down to 14,700, we'll round it 748 people. So about 14,748. Okay, and now the last part, they want to know when we want to reach 12,000. Well, it's definitely longer than 10 years because the population hasn't dropped enough yet to get to 12,000. Where is the 12,000 going to get plugged in? Alexis, what do you think? Where's the 12,000 going to get plugged in?
For
A of t, yeah, it's an amount of people. So we're going to fill that in on the other side, which means your variable is in the exponent. So we have to start thinking how we're going to deal with that. So 12,000 people equals 20,000 times 0.97. The t. All right. What can we do first to get t by itself? Yeah.
Divide both sides by 20,000.
Yeah. Divide both sides by 20,000. So that's gone. All those zeros are gone. And 12/20ths is going to reduce to. You tell me what's 12/20ths. 0.6 because that's 6/10, or let's just leave it as 3/5. Yeah, we'll leave it as a fraction. So 3/5 equals 0.97t. All right. Now, how do we fix that so the t isn't in the exponent? We did it two ways today, but we don't need to do it both ways because if we do it the first way, we have a new formula, that change of base formula that's going to help us.
Do the log x over log y.
Okay, so we do have to convert it into a log equation and then apply that formula.
Yeah.
What's my log equation going to be first?
Log base 0.97 3.5. No, they're not 3.5. 3/5
Yep, 3/5 is my argument,
equals t.
and that equals t. Now we just need a way to type that in because we didn't used to have a way to type base 0.97. Now we do. How do we type in that into the calculator? Yeah.
It would be log base 0, not base, argument 0.97.
Well, that's in the bottom, so that's going to go in the bottom.
Oh, okay. Then it's the 3/5.
So the log of 3/5. Yep.
Divided by the log 0.97.
Log 0.97. Okay. So let's figure that out, and then that'll tell us how many years have to pass before we hit 12,000 people. So log of 3/5 divided by log of 0.97. And it should be more than 10 years because we did 10 years and that only got us down to 14,000 something. So it's about 16.77 years. To reach, what was it, 12,000 people. Now, we are assuming that the same number of people, same percentage of people drop every year. If it changes from 3%, then this wouldn't be accurate. Okay, but we're going to assume the 3% is constant. Okay, so the next one, they've given us two problems. One problem has the variable in the base, the other one has the variable as the argument. But in both cases, we're going to do the same kind of thing to solve it. What format are both these equations in out of the two that we studied this week? Yeah. Yep, they're both in log form. And what can we do with something that's in log form to try to solve it?
Put it in exponential.
Yeah, let's put it in exponential. What, for the one on the left, what is my base?
X.
My base is x. What's my exponent? Yep. Yep, logarithm always equals the exponent. And what ends up by itself on the other side? Yeah, 5, that's your argument. Okay. How would you get x by itself there? And get rid of that 13th power? Yep. Or no? No.
Well, wouldn't you like 13 it? I don't know what you say.
Can you say it again?
You would take like the 13 like root of it.
Yeah, take the 13th
That's what
root.
she meant.
Okay, that's what I meant. I was like, I don't want to say that. Okay, thank you.
So yeah, we're not taking a square root or a cube root, you're taking a 13th root. If I ask for a decimal, do people know how to type that in, the 13th root of 5? No? So on the calculator, that's where you have to put your index in first. And then math 5. So that's how you do a third. That's how you do any root. You don't have a button for it. And then just type in 5. So it's about 1.13. But you can also leave your answer if they don't ask for the decimal. Yeah, just leave it as the 13th root of 5. All right, so that's solving where the variable was the base. How would we rewrite the one where the argument is now the variable? Yeah. Yeah, just tell me the whole thing.
3 to the 7 equals x.
Yeah. So for that one, 3 is the base. Logarithm always equals the exponent, so that's the 7. And now that's your final answer. That would be small enough that we could reasonably do that out on the calculator. I mean, it's not a huge number. If it was like 3 to the 200th power, then I'd say no, we're not going to do that. But that's 2,187. Any question on either one of those? Okay. All right, so the next problem we're going to look at is simplifying logarithms. And for this one, they all have some kind of special property that lets you do it very quickly. Let's start with the first one. Log base 6 of 1. What does that come out to?
0.
Right, that comes out to 0. If you were to write that in exponential form, 6 is your base. The exponent you don't know, that's what you're solving for. But you have to raise 6 to a power and get 1. The only power you can raise 6 to and get 1 is 0. All right, how about the second one? Log base 2 of 2 to the 5th power. Everyone remember what that one simplifies to? Well, if not, what's my base there? 2. Which 2? Can you give me a color? Yeah, the red. So the red 2 is my base. And we're solving for the exponent. We don't know that. That's like if you set it equal to x. We don't know the exponent. But what would go on the other side by itself? Yeah.
32.
What is it?
32.
Let's,
Oh, 2 to the 5.
yeah, leave it as 2 to the 5th. I think that's going to make it easier to see the answer. So now what value of x would make the left side the same as the right? Yeah.
5.
5. Yeah, that's a really long way to do that one. We just want to remember when these two numbers are the same, the answer is whatever I just circled. Okay, it's 5. And how about this one? Log base 8 of 8. This is where the base and the argument match.
X.
Yeah, this would come out to 1. Okay, and if you forgot, you could think of it as this is your base, x is your exponent, and the argument goes on the other side. What power can you raise 8 to get the same thing back? First power. So those are all properties of simplifying logs. All right, so for the next one, we're going to be given a table of data. You don't have to figure out if a power model is appropriate. I just want you to find a power model no matter what. Okay, so find the power model. So we have a table of data. What's the first thing that we have to do with that data? If we're going to find a power model. Yeah? Well, that's if we want to check to see if we should find a power model. But we're not going to check it. We're just going to do it. So if we were going to check it, yeah, we would do that first. But what's the first thing we do with that data if we want to find a power model? Yeah.
Find the ln of x and y.
No, that's not. Yeah, that's what Laura said. That's only if you want to check if it's going to be a power model, right? So in class, I did. I checked if we should do it. I already know that this data is a power model because I already know because I made the formula to make it. So yeah, what's the first thing we do?
What?
Oh no. Yeah.
Don't you have to like find the A and B
We do, and how are we going to find the A and the B?
on the calculator?
On the calculator. So then what do I have to do?
You go to stat,
Yep.
calc, and then you go to,
We can't do calc yet.
no?
Well, not really, no. What do we have to do before we go to calc? Yeah?
The numbers in the table.
Right, we have to put all those numbers into the table.
I created that.
So, stat, edit, and magically I just already have them in the table. So that's really handy. On the test, that probably won't happen. You'll have to type in different numbers, but you'd have to put in all your numbers. Okay, so now we've got all the data in the table. What do we do after it's in the calculator? Remember, after it's typed in, this was step 2 on the notes. So step 1, we checked if the data was appropriate. We're not doing that step. Step 2, after you type the data in, yeah.
Now you go to stat, calc, and then go to power rank.
Yeah, so go to the power regression. We hit enter, and we put our x's in L1 and we put the y's in L2. So there's nothing that we need to change. So what do I do from this screen? Yeah,
You go to calculate.
go to calculate. And it just so happens that it found an equation for the data that is perfect. You can't get better than an R value of 1. It's an exact perfect equation. And that's because we picked the numbers to be that way. So how would you write your power model for this data?
Mine didn't come up with having like the R squared and the R.
Yeah, that's okay.
Okay.
Yeah. The R is there to tell you how good of a model it is, but unless you turn that on, it won't show up.
Oh, okay.
Yes.
Is it 12x to the 1/2 or 0.5?
12x to the 1/2, and don't forget your y equals. That's the equation that represents that data. 12x to the 1/2. Okay, any questions on how to get that? Yes.
I don't know if you already went over this, but what happened to the ln of the x and y? You already see it.
the ln?
Yeah.
So the only time you take the ln of everything is if you want to actually check, should you be doing a power model? On the test, I want to know if you know how to do a power model, so I wouldn't give you a data set that wouldn't work. So I'm just going to say, here's some data, find a power model.
Wait, so don't do it on the test then?
The ln?
Yeah.
No.
Okay.
All right, so the next two questions are what we did today, taking logarithms and either combining or splitting them. Let's start with this top one. When we split that, are we going to have 2 logarithms, 3 logarithms, 5 logarithms? How many logs are we going to have when we split that up? Yeah. Well, we can start with 2, but it's going to turn into more than 2. So when you're splitting it, if you have a fraction, let's deal with the fraction first. All right. So when you split it and it's a fraction, does that split as addition or subtraction? That's subtraction. So we're going to have 2 logs being subtracted. What's going to be the base on each log? Log base 3. Yeah, so the base will be 3. And I know we got a little more work to do with it, but what's going to be my first argument for now? Yep.
5 log 3 of 4x.
We'll come back to splitting it up. Let's just leave the argument the way it is right now. So what's the argument before you do all that?
Like you can just bring it down.
Yeah,
Log 3 of 4x to the 5th.
log base 3, 4x to the 5th, and then minus log base 3. What's going to be that last argument?
Minus log base 3 of y.
Minus log base 3 of y. So the last part's done. There's not really anything else we have to do with that. But we do have to simplify the first log. How can we split log base 3 of 4x to the 5th? We can split that as a sum or a difference? Yeah, that's going to split as a sum. So we're going to have 2 logs. Both of them are going to be base 3. The log at the end is done. What would be my first log? Log base 3 of 4. Yep. Plus, what would be my second log? And just make sure we follow what the directions are asking. Yep.
5 log base 3 of x.
5 log base 3 of x. Yep. So that's how you take a single log and split it into multiple logs. All right, and this one is reversed. We're going to combine this into a single log. What's the first thing we would have to do here on each part of the logarithms, or each log? We have to do what?
Give the arguments their powers.
Yeah, take the argument and put the 3 back as the power, and take the 4 and put that back as the power. So we're going to have log base 2 of 6 cubed plus log base 2 of 5 to the 4th. All right, so we put the powers back, but now we have to merge that into a single log. What is the base when it's all back together? Yeah,
2.
it's going to be a base of 2. And what are we going to do with our arguments? 6 cubed and 5 to the 4th. Yeah,
You can multiply them.
we'll multiply them. So it's 6 cubed times 5 to the 4th. And if they asked us to do it out, we could do that out. It's not like horribly huge, but a little bigger than I can do in my head. So any questions on how to take those logs and recombine them? All right, so last one we'll look at is just solving another exponential equation. This time we don't need to change it to log form because the way the numbers are, it's going to work out nice, the nice answer. If it was this, what would the answer to that problem be? 3 to the x equals 9. Yep. Right, this would be 2. Our problem is a little bit different. We don't want to get 9, but we want to get 9 and we want it flipped. So what kind of exponent does that mean you're going to have? Right, so this has to be a negative. And in this case, it would be negative 2. Yeah. So just make sure you understand your properties of exponents and that if you write a negative, it causes it to flip.